So we are working exclusively on L2R. We are working on L2R. Okay, our Hilbert space is L2 of R. Okay, which is all square integrable function with respect to Lebesgue measure. Okay, and this we identified with the Fock space, the gamma of Cn, which is the symmetric Fock space. That's the only Fock space we are using. Symmetric Fock space of Cn. If we needed, I will recall the definition again. But in this class, we don't really need those definitions. So I'm not. We only need the Weyl commutation relation and Stone-von theorem for whatever we are going to prove today. Okay, so I don't want to recall each time gamma of Cn. If needed, later when we use that picture of Fock space, we are going to use the L2 picture of Fock space. There are two pictures of Fock space. Sorry, this is L2 of Rn. I'm sorry. This is L2 of Rn. All square integrable function. This is equal to all those f from Rn to C, such that integral mod f square is less than infinity. Okay, that is the L2 of Rn, and that we identified with the symmetric Fock space of Cn. Okay, the finite dimensional vector space Cn. Then we defined some vectors E of Z, and that is how we identified these things. We defined some exponential vectors in L2 of Rn, which are some functions, okay, which are in functions given any Z for Z in Cn. This is for Z in Cn. Okay, so for any Z in Cn, we defined exponential vectors in L2 of Rn. Similarly, we can define exponential vectors in gamma of Cn, symmetric Fock space. There is a unitary map which takes these exponential vectors to that exponential vectors, and that is what we extended. That is why we identify these two spaces, and we always treat these two spaces as same. We don't want to use a unitary between them. Okay, whichever the picture we take, we use that. So then on those exponential vectors, we define the Weyl operators. Okay, the Weyl operators are defined like this. If we have a Z in Cn and alpha also in Cn, then W of Z acting on E of alpha is equal to E of, this is a norm, the finite dimensional norm Z squared by this. Then Z alpha, you take this is a scalar, we are taking it out, and this is again the exponential vector. It takes one exponential vector to another, it translates the exponential vectors, but that is not unitary, so we have to multiply by some scalar to make it unitary. So this becomes a unitary. Okay, so these are all Weyl operators, and these Weyl operators satisfies the following. So this is what we need. Okay, so we have this Weyl representation. So we have this W of Z. I'm just recalling what we did last time. Z in Cn. Okay, this is contained in our B of H. B of H. Our H is L2 of R, which is also same as gamma of Cn, and contained in B of H. These are all unitaries. Okay, unitaries, and they satisfy this Weyl commutation relation. That is W of Zn, W of Z2 is equal to e power, this is a number, imaginary part of Z1, Z2, okay, W of Z1 plus Z2, okay, Z1 plus Z2. Okay. I mean, if you apply it again for Z2 plus Z1, this just says that W of Z1, W of Z2 equal to e power minus I 2 times imaginary part of Z1, Z2, just the inner product between the imaginary part of that, W of Z2, W of Z1. Okay, so they commute up to this scalar. Okay, W of Z1 and W of Z2 commute up to this scalar. So the point is, if the imaginary part, inner product of the imaginary part of the inner product between Z1 and Z2 is 0, okay. For example, both Z1 and Z2 comes from the real, I mean, Cn is Rn plus I Rn. You can, I mean, it's just a complexification of Rn. Okay, you can consider it like that. It's a complexification of Rn. Suppose you have the Z is coming from Rn itself. Z1 and Z2 both are coming from Rn. Then they commute. Okay. Similarly, both Z1 and Z2 coming from I times Rn. Okay, in the imaginary part of the Hilbert space, then also they commute. So it only depends. It depends on the imaginary part of the inner product. If it is 0, then they commute. Okay, so when you have a commuting family, then I mean it is just the classical probability. So if you have an Z1 coming from the real part, if you have a Z1 coming from another Z coming from the imaginary part, then there is a commutation relation. And I mean the one comes from the real part is usually called as the position operator. one comes with the imaginary part is called the momentum operator. I mean, it corresponds to orthonormal basis, but basically this is what, I mean, if you have one dimensional, this is what it means, okay? So it's basically the classical probability, except that you have this commutation relation, and this gives the complication, that's all, okay? This gives the quantum curve. So then we have two properties of this Weyl commutation relation, which we have been using, and one of them we proved last semester, but we will go through a proof again. That proof is not satisfactory, so we will go. I mean, that uses unbounded operators. We will make it more clear. Okay, we will have a different proof. So one is, if you take W of Z, Z in Cn, you take all of them, and you take the span. You take the linear combination of this. Taking linear combination is same as the algebra generated by them, because product of two Weyl operators is scalar times a Weyl operator. So you just have to take linear combination to consider the algebra. You take the span, and then you take the closure in the strong topology. Strong topology. And that is equal to all of B of H. So what is strong topology? Strong topology. I take what is strong topology. I recall what is strong topology. I mean, these are all not metrizable topology. You have to use nets to deal with the topology, but mostly sequences are enough for us. Okay, we will deal with only sequences. Okay, but usually when you take the closure and other thing, you have to deal with nets. Okay. So, but when you deal with bounded subsets of BFH, then sequences are enough. They are metrizable on bounded subsets. Okay. So I have to use net. So T lambda converges to T in strong topology if T lambda xi converges to T xi for all xi in H. Okay. Point-wise convergence. It's just point-wise convergence. That's called strong topology. It gives a topology. Okay. So those things we have seen last semester. So this is one thing, and this is equivalent to saying, this span closure is equivalent to saying, you take W of Z, okay, Z in Cn. You take the commuton, all operators, commuton. By that I mean it's a commuton. All operator with commutes with this set. You take the commuton. When I put the dash like this, it means the commuton. The commutant of this is scalar times identity. This is equivalent to that. So this is the first condition. This is what is called irreducibility. Of Weyl representation. Okay. This is what is called Weyl representation. Also, it's called the relation, whatever we wrote, that's called canonical commutation relation. Okay. This is the canonical commutation relation in Weyl form. Usually, there is a relation satisfied by the creation annihilation operator or the position momentum operator. That is what is called usually as the canonical commutation relation. This is it's exponential form. We have seen that also, but we will come to that later. Okay, this is what is called canonical commutation in the Weyl form. Okay, that relation, that commutation relation we have written, that is the canonical commutation relation in the Weyl form. So this is the irreducibility of the Weyl representation. The second thing, which also we are going to be proved. Okay, we will prove this. Is if there exists a U from some Cn to some B of K, some other Hilbert space, C of K, U alpha, sorry, alpha going to U alpha, U alpha, a strongly continuous. It's not a representation, a strongly continuous map, let us say map. I mean, it's not a representation, it's a projective representation. What is projective is just defined there. Okay, if it satisfies the property we are going to write down, it's a projective. Projective is more, it has to be a scalar. Here we will use here the scalar will be specific. Okay, strongly continuous projective representation. Okay, strongly continuous means if alpha n converges to alpha in Cn, okay, then U alpha n converges to U alpha in strong topology. Okay.
So K is like the compact operators or
Say?
K is supposed to be the compact operators of H or
no. It is some other Hilbert space. Some Hilbert space. Okay. Compact operator is not a Hilbert space.
I know that. Yeah. That's why.
Yeah. It's no. We haven't fixed any notation for compact operators. K is some Hilbert space. I am saying you have another unitary representation, another Weyl representation. another representation satisfying this commutation relation, then it is unitarily equivalent to that. That's what I'm going to say. Okay. So you have some, there exists a u is a function, alpha going to u alpha. Maybe you can put like this, okay? Maybe alpha going to u alpha like this, okay? If you want, you use whatever subscript or the u alpha, okay? Which is a strongly continuous projective representation satisfying the same Weyl commutation relation. That is u alpha prime equal to e power minus I imaginary part of alpha prime, the inner product, then u alpha plus alpha prime. Same Weyl relation, it satisfies. Okay. Then there exists a Hilbert space. This K is a Hilbert space. Okay, that's what you asked. That's a Hilbert space, some Hilbert space. B of K, I mean, we fix this notation. B is ball bounded operators on K. Okay, B of K. Then there exists a Hilbert space. I mean, we use small letters because it can be infinite dimensional, but we use small letters to show it's a small Hilbert space when compared to the Hilbert. Then there exists a Hilbert space, small k, okay, and a unitary. A unitary means you can just assume those two spaces are same. Okay, V from L2 of Cn. Wait a minute. So n I have used for the sequence. That's a different n. Okay, maybe you use alpha k or something for the sequence. Alpha n goes. Yeah, I should use a different letter. Usually that is why we use C power D or something. It's better to. I mean, there is a n coming here. There's indexing set for sequence. That's different. Okay, don't. There is no confusion. L2 of Rn tensor k to this k, such that V W of Z tensor 1, okay, V star is equal to, I mean, maybe alpha I put, equal to u alpha. Okay. Okay. So you can assume that space of u, and such a unitary is, I mean, it's unique. It's a, this is up to unique up to, I mean, such a k, and I mean, and this representation, all these things are unit up to unitary. If you have a different space, there will be unitary between them, which is not twice all that. Okay, there is a, so this is unique up to unitary. Okay? We will prove this later.
So,
yeah.
In this one, why are we taking the maps to some bounded operators on any Hilbert space? Wouldn't it make sense to take some bounded operators on some Fox space or some Hilbert space and then?
No, but you haven't understood the point of the theorem. The theorem says if you have some abstract Hilbert space and if you have some abstract representation, u alpha going to u alpha, then it is unitarily equivalent to this. What do you mean by taking that? You can actually take is what his theorem says.
Yeah, I mean, we are taking like operators on any arbitrary Hilbert
You
space.
have some arbitrary Hilbert space,
Yeah.
and you have arbitrary representation alpha going to u alpha, which satisfies the Weyl representation, arbitrary Hilbert space. Then it is unitarily equivalent to the Weyl representation. That is what this says. But how can you take it to be initially Fox? This is for any arbitrary. There is no other. This says the Weyl representation is unique up to that multiplicity, whatever that multiplicity space is, that k. Okay, up to some amplification, Weyl representation is unique. That's what it says. Up to some amplification and unitary, the Weyl representation is unique. Since I have antibiotic, my tongue is having some. I'm not able to. Otherwise, also I have a problem in pronouncing something.
Okay.
No. What is the problem? What is the question?
No, my issue is that we initially defined Weyl operators on like Fox spaces.
Weyl operator is specific, concrete operator defined on Fox space.
Yeah,
They satisfy the commutation relation.
yeah.
Now you have some other unitary u alpha, collection of unitary u alpha, which satisfy the same kind of commutation relation. Then that is equivalent to this.
Yeah, but like there is the Fox space coming here.
Oh, this is the L2Rn is a Fox space. Oh, you can replace it by gamma of Cn if you want.
Achha, okay.
I said no, gamma of Cn and L2 of Rn are same for us.
Yeah.
Okay, if you want, I can use the
No, I think that's
I
fine.
can just use H. Okay, what I supposed to use is I can just use H. Where is the camera? Camera is here. No? Yeah.
Okay, I think I get it.
Hmm?
I
No, this is Fox space.
Yeah.
That is why I said W of alpha. W of alpha is acting on Fox space. So I should use H. Okay, we call H as our Fox space or L2 of Rn. Doesn't matter. So I should have used H, as we said. You are right. Okay, H. Okay.
Okay.
That's why I'm using K for the other one. Okay. Because H is fixed for L2 of Rn. Okay. Now it's clear?
Yeah.
This, the Weyl representation is unique. And suppose if the U alpha is reducible, I mean, if U alpha is irreducible, that is, you take the span closure in the strong topology. So suppose, so this corollary to this, okay, suppose the span closure U alpha, you take alpha in Cn, okay, and you take the span and the closure in the strong topology is equal to the B of K, okay, then there is no K, that small k is not there, then K is equal to C, okay. I mean, the space, actually the K is nothing but same as the Fox space. You can, I mean, there's a unitary between them. You can forget the unitary. You can identify these two spaces with the unitary. Okay. So if it is, I mean, if it is irreducible, what will the W of alpha or U alpha will generate? U alpha, if you, I mean, see this map, no, this V something V dot this add V, this map is there. No, this is a very nice map. We have talked about it earlier. This add U map, add U of T is equal to UT U star. This map is a very nice map. It is continuous in all possible topologies. Okay, and it takes inverse to, this is a representation. Okay, so if you identify two Hilbert space with unitaries, you can identify the B of H and B of K, the corresponding operator space, operator algebras, using this add U map. Okay, so this way W of alpha you can identify with U alpha if it is irreducible. Okay, but if now we are identifying with W of alpha tensor 1 with U alpha. So what is the, I mean, what is W of alpha tensor 1? What will it generate as an algebra? Take the algebra and take the closure. It will generate B of H tensor 1, right? All operator B of H tensor 1. So if it is irreducible, B of H tensor 1 this should also be reducible. Okay, if this side it is reducible, this side also it is reducible. That will mean that H is same as K up to unitary, up to this unitary. Okay. I mean, it's important that there are many unitaries. We have a particular unitary and we are identifying them. Okay, we're identifying these two spaces. When we identify L2 of R, Rn, and gamma of Cn, we have a particular unitary taking exponential vector to exponential vectors, not some unitary. Okay, that is how we are identifying. We should keep in mind how we are identifying. Okay, I mean, just we don't have to write each time the unitary. Okay, so this says the Weyl representation is unique. Okay, up to some amplification. And there is no amplification if it is irreducible. Okay, so that's the theorem. Okay, so now we define another one. If you fix a Z, so if you fix Z in Cn, then W of T is at T in real line. Okay, this is a unit, one parameter unitary group. Okay, strongly continuous. It's important it is strongly continuous unitary group. So there exists a self-adjoint, unbounded, of course, possibly unbounded P alpha, okay, on H, such that W of Tz equal to e power I T P alpha. Okay. This is Stone's theorem. This is what is called Stone's theorem. Stone should be in capital. Is Stone's theorem. Okay. Okay. Now, if rho is a state, and I'm just recalling on H. I mean, rho is a state on H means using rho is a trace class operator with trace 1. That's all. For a state is a density operator. It's just trace class operator with trace 1. Is a positive trace class operator with trace 1. That is our state. That's how we define the state. And if we have a state on H, by this we mean, I mean, for earlier our definition of state is it's a linear functional on a algebra. The algebra here is B of H, and this row will give a linear functional through the actual trace. Okay, so that is what we are using. But for us here is state row is a state on H. Then it gives a distribution. I mean, P alpha will look like this, right? P alpha is equal to e power minus, e power x. Itx is for that. E power x d, I mean d, I use e, okay? E is the, because there's p there, I use d, dx on Rn. Okay, where e from e is the spectral measure. This is Borel sigma algebra of Rn to B of H. Projection valued. It's a projection valued measure. Okay, this is a spectral measure.
So like Z should be alpha.
Wait, which
Like W of P alpha is
yeah. Z should be alpha. Maybe I can change it to Z here. Oh, in both the places. Okay. Yeah. Alpha, then we change it to alpha here.
So how did you get that? Like P alpha has unit trace?
P alpha?
You said
P alpha nahi. The row has unit. P alpha is an unbounded operator. There is no trace on them. There is no trace on them. It's an unbounded operator. Okay. So P alpha has this representation through spectral measure. Okay. And you have, this is a spectral measure. Then this row gives a measure on this. See, there are many measures you have a spectral measure. So if you have a vector, any vector in H, then you can get a probability measure on this, or you get a measure on this. So, but when you have a row induces a probability distribution on real line. Okay. So row induces that, which is the corresponding probability, which we call as the probability distribution of this random variable P alpha. Okay. So we get a probability measure. There exists a probability distribution on R, okay, on R or BR, defined by so probability distribution is called mu. So mu of E equal to trace of row, that E of, I should use mu of A. Sorry. E is a set, E is the spectral measure now, so I should use A. E of E. Okay. E is a spectral measure. So V of A is a projection. So trace of that row E of A is a mu of A. And since that is the spectral measure, this will be a probability measure. I mean, since the trace of row is 1, because of that, it will be a probability measure. This gives a probability measure on real line. Okay. So this is what we call as the probability distribution of this random variable P alpha. Okay. Now further, it's also true that, I mean, we have used the functional calculus. So this is the assignment I want to give. It's a very only, I mean, if when you write it, you will just get, I mean, it will be clear. All those measures, everything will be clear. Okay. So prove, I mean, okay, before that, let me define what is a characteristic function. Okay. So if I have already defined, if mu is a probability measure, on R or Rn, on Rn, let's say, I mean, it may be Rn or R, okay, then mu hat of any x is in Rn, okay, is equal to e power minus it, mu hat of, it's a single variable, you should, okay, I will use single variable, okay. Mu hat of t, okay, itx d mu x. This is the characteristic function of any probability measure. Okay. So the assignment is show that mu hat of, for this mu, okay, this is for any mu. Okay, for this mu, whatever the mu we have defined, You have a state, you have the random variable P alpha, then you have a probability distribution, and mu hat of that T, okay, mu hat of that T is equal to trace of W of T alpha rho. Okay, that's all. Last time itself I mentioned this, but there is you need some small proof. Suppose this rho is a pure state. Okay? It's given by a single vector. It's a pure state, means it's a rank 1 projection. Okay. Then you have, see, if you have a spectral measure, then if you have a single vector, then you have get a measure on that. So it will be with respect to that measure, then you can get it. I mean, you can prove it. When rho is a rank 1 projection, you can prove it easily. Okay. Then any trace class operator can be approximated by finite rank operator. You can use that. Then you have to use the approximate convergence, I mean appropriate convergence and all that. Either you have to do that, or trace, you can use the expansion of trace and try to prove it. Okay. It's not difficult to prove. Okay. So this is an assignment one. I have already given an assignment for the map between gamma of Cn and L2 of Rn. So this is assignment 2. Okay. So the classical theory, there is this Bochner's theorem. So if we have a f from Rn to C, okay, such that f of 0 equal to 1 and f is positive definite, okay, that is positive definite. The meaning of positive definite is, maybe I'll write here, for all C1 up to Ck, there is n already there, Ck, and x1 up to xn, xk in Rn, okay, summation Ci bar Cj f of xi minus xj, I think. Okay, this is greater than or equal to 0. So this is the definition of positive definiteness. Okay. So f is positive definite, f of 0 equal to 1, and this is the meaning positive definite. Okay. And f is continuous also. Okay. Then there exists a measure mu on Rn such that mu hat T is equal to f of T. Okay. Oh, this is T is in Rn, so I think it's okay. So this is the classical Bochner's theorem. We want to prove a quantum analog of this. So we want to first define, we have already defined last class. I will recall the definition of quantum characteristic functional. And then we want to prove a quantum analog of this. Okay. So what is quantum characteristic function? Definition. Quantum characteristic function. Okay. So rho is a state. So this, the characteristic function is for a probability measure in the classical case. Here it's for a state. State on H. Okay. Then rho hat of alpha for alpha in Cn. Okay. Rho hat of alpha equal to trace of rho W of alpha. Okay. So you will see that if you fix an alpha and if you consider rho hat of T alpha as a function of T, then that is the actual characteristic function of the measure, the probability distribution of P of alpha, P alpha. That is the assignment which says here. The assignment says is mu hat T is equal to W of T alpha rho. Right? mu hat t equal to w. Here t is the variable, alpha is fixed. Okay. So this says that the mu, this is the characteristic function of the distribution. I mean, and the rho generates a distribution, okay, on the real line. Okay. And it is just that the characteristic function of that distribution is this mu hat. Just say, and the quantum and classical are same when you restrict to one single random variable. Okay. So here you have p alpha. If the alphas comes from the real part Rn, that is still classical. You will have a, I mean, it is just a multivariate distribution on Rn or something. It's like that. Okay, but you include the imaginary space also. When they don't commute, then only the quantum picture comes in. Okay. Okay. So this is how the characteristic function is defined. Okay. So then what we observation, maybe I will state the theorem itself. Okay, theorem. So this is the quantum Bochner's theorem. I don't know who proved it, because physicists have been using this. The proof is in for KRP's paper, but as far as the paper is not, I mean, it just collects. I mean, I think KRP wants to write that paper so that he can do more work. He can, I mean, he wants to write more papers on that. He wants to, but then there is no clear literature anywhere available on all these things. But with this characteristic function being used by physicists for a long time. So I think there must be a proof for something. There is a proof for something is not clear. Okay. So possibly KRP proved it, or it is the proof is there already, but it is being used for a long time. Without proof or with proof, I don't know. So the theorem. So this is the quantum Bochner's theorem. So suppose f is a function, some function. F is a function from Cn to C, okay, and such that satisfying f of 0 equal to 1, okay, f is continuous, okay, and there is a small change. Okay, earlier Bochner's theorem says that if it is positive determinate, then it is given by a measure. Here some imaginary part of the inner product will come in, such that this k alpha beta. Okay, I said positive definite can be defined for two variables. It is actually defined for two variables. I mean, here it's all multiple by two variable means this alpha beta. This function itself is multivariable. It's in Cn. Okay, so k alpha beta equal to e power I. Here you have minus sign here. If you have alpha beta, I think there's a minus. We'll check it. Okay, I think there's a minus sign here. Imaginary part of alpha and beta times f of alpha minus beta. Anyway, if we will do the calculation, and if you want, we will change the theorem. Okay, whether there is a minus, where the minus is, let me just check. Okay, I can look at the paper, but we will do it. Okay, is positive definite. And so for two variable I will write, that is for all C1, so C alpha 1 up to alpha n in Cn, and C1 up to Cn in C alpha k. Okay. Please don't mind. Sometime we have fixed the n for our Hilbert space, but I may be using n somewhere else, but that n is different. Okay. Ck summation Ci bar Cj f of k of alpha I alpha j is greater than or equal to 0. That is e power. So that is, maybe we can write it. That is summation Ci bar Cj e power. We just need an e power there. E power minus I, imaginary part of alpha I alpha j f of alpha I minus alpha j is greater than or equal to 0. So if it is positive definite, if it is continuous and f of 0 equal to 1, then it is a It's a characteristic function of a state. Okay, so that's what we want to prove. So this way we want to prove. So suppose rho is a state. It's a state on L2 on H. Okay, and rho hat the characteristic function. Okay, then we want to, then it's clear rho hat of 0 equal to trace of rho W of 0. W of 0 is identity, so trace rho equal to 1. So it's clear rho hat is 1. Okay, and continuity you want to check. The continuity is, suppose alpha n converges to alpha in Cn. Okay, then what do we have? We have already proved in the last semester W of alpha n converges to W of alpha in strong topology. Okay, then here comes the exercise. See, this was a problem in the other course, graduate analysis course. Did you look at the question paper? Okay, let me recall here. Okay, this was a problem. Maybe you do it as an assignment here. The problem is, if Tn, suppose you have a sequence, okay, Tn contained in some B of H, okay, such that this is the I use that notation there. Inner product was linear in the first variable here. So xTn y converges to xty. Okay, you have a sequence which converges to, so T is an element. Okay, then for any trace class operator T, trace class operator rho, sorry, rho, trace of rho Tn converges to trace of rho T. I gave it in the graduate analysis course because it uses the measure theory part. I mean, what is there? The inner product converges. Trace is a infinite sum of some inner product. Possibly, I mean, if it's infinite dimensional. Finite dimensional, there is nothing. It's an infinite dimensional. Trace is an infinite sum of inner products. So each of the summand will converge, right? You have to show that the whole thing converges, but you can't say that. I mean, you need some justification. You have to use, how will you say, some infinite? You have a series, okay? You have some two variable thing, x and k, something. Okay, each x and k converges to some xn. When as k converges, the sum is over k. Okay, you want to say the sequence series itself converges. How will you justify? What will you use? Huh? In measure theory, there is something. Correct. Dominated convergence. Yeah. It's just dominated convergence. Just dominated convergence theorem. Okay, it is just an application of dominated convergence theorem. So this also I give it as an assignment. Okay, assignment. Please note. You prove this. If that converges, then this happens. Okay. In particular, if some Tn converges to T strongly, then this inner product will converge. Strong convergence will imply that. So we have W of alpha n converges to W of alpha. So this implies this. This implies trace of rho W of alpha n converges to trace of rho W of alpha. That's all. Okay. This follows from this exercise. Okay. Okay. So please do this. This is just one line. You just have to justify. You have to find a bound, uniform bound for that, which will be clear from the row. Okay. Then you have to use dominated convergence theorem. Summation is like an integration, no? So you remove the dominated convergence theorem, you remove the integration. That's more complicated. This is easy. So you have to use the dominated convergence theorem and then bounded, whatever it's called, bounded convergence theorem or called dominated convergence, whatever. Okay. You use that and you get this. So anyway, you write it, better you write it. Okay. Okay. We are going to use this, whatever recall, this fact again and again here. Okay. We may use it because we want to take convergence inside the trace. Okay. You can't take norm convergence. Norm convergence does not imply trace class convergence. Okay. Can you see why? Because the closure of finite rank operators is compact operator. Okay. But then the closure that trace class is a proper subset of compact operators. So norm convergence will not imply trace convergence. Trace convergence will imply norm convergence. It's the other way. Right? Correct, no? Sometimes I also get confused with this. So because the closure is smaller, trace is stronger. Okay. There is an inequality also I proved, if you remember. Trace is smaller than the norm. Trace of ST is smaller than norm S times norm T. Okay, because of that. Okay. So because of that, it will be. Okay. So you just use that. So this implies this goes to this, and this is what is called rho of alpha n, rho hat of alpha n converges to rho. This is equal to this. This is equal to rho hat of alpha. Okay. So our characteristic function is continuous. Okay. This follows from the Weyl law. Weyl representation is strongly continuous. It follows from that. Okay. That is one thing. So this is continuous. So there are three conditions. First condition is f of 0 equal to 1. Oh, sorry, this is f. I'm sorry. I confused it. Oh, no, this is no f. Sorry, sir. This is rho. We are proving one way, this way. That is, we have a rho which is a state on that. Rho hat is our f. So rho hat of 0 is this. And we proved that rho hat is continuous. Now we have to prove it's positive definite. I mean, that whatever the imaginary part, whatever is positive definite. Okay. So let X be summation.
Essentially, this side of the theorem is telling you the properties of the character.
Correct. Properties of the characteristic function. And if it satisfies those three properties, it actually comes from a state. So otherwise, non-trivial. We have to produce a state. Okay. Okay. So suppose X equal to summation. I don't know why this pop up all the time. I don't know. I touch somewhere.
Software is not good.
This?
Software is not good. I'll give you another software later.
Okay. For iPad.
Yeah.
Okay.
The software is very buggy.
Yeah. No, I had to buy something. For that, I need some international card, which I don't have. My card is not working in the this store.
Oh.
Yeah, that is why there is some notability, something, and that may be better, I think.
Good notes is there.
Good notes, something that's free. No, you have to buy it, no? Yeah, I was not able to buy with my card.
Okay.
Yeah, it was. Anyway, all these things are recorded, so it's okay. So let X equal to I equal to 1 to K Ci. Okay, W of alpha I. So you just take this operator. Then we know that X star X is greater than or equal to 0. Star is the adjoint. Okay, X star X is greater than 0. Okay, so this implies trace of rho X star X is greater than or equal to 0. Right? I mean, you know why this is true. Trace takes positive. Trace is a positive linear functional. Trace take positive operator to positive operator. But whatever we have, rho of X star X is not positive operator. But you can write this as rho power half. Rho is positive. So there is a square root for that. X star X, rho power half. You can take this rho power half. By the tracial property, you can take it that side. Okay. So this I did last time. So because of that, this is true. In any case, when we define a state, it has to give a positive linear functional on some algebra. That is how this is. I mean, we are not going through that definition of state, positive linear functional on that. We are having rho as a state. I mean, as a trace class operator of trace 1, positive trace class operator, and it is a state because it gives rise to a positive linear functional through this. Okay, that is what you're using. Okay. I mean, that definition we have to use because that is the actual generalization of the classical probability to quantum probability. Okay? That's why. Okay, so trace of this is greater than or equal to 0. But now this is nothing but X is summation of something. So this is equal to trace of, we can take the sum out. Trace is linear functional. Summation Ci bar Cj. Okay, Ci bar Cj. W of alpha I. Sorry, rho is there this side. Rho of W of alpha I star W of alpha j is greater than or equal to 0. But W of alpha I is minus, right? W of minus I, alpha I. The star is minus of that, right? So W of alpha j is greater than or equal to 0. But that is equal to summation C bar Cj trace of, so what is that? Rho e power minus of minus that. So it will be plus, right? So it should be plus there. Is it right? Or I can. So it should be plus. Okay. I summation alpha I alpha j. Minus alpha I will come out of this. So there should be imaginary part. Okay. F of alpha j minus alpha I is greater than or equal to 0. There are two corrections to the theorem. Please note. First one is this is beta minus alpha, not alpha minus beta. And this should be plus. Okay. Please change the minus to plus in the theorem. And it is beta minus alpha. Anyway, let me look at the paper to make sure I'm correct. So, we don't have it here. I have to open it from. Okay, I'll check it. I think it's okay. We just calculated it, right? So our calculation is correct. Okay. So it is plus here. Is it okay? It's right, no? W of alpha I, which is minus alpha I and alpha j, and which is going to be alpha j minus alpha I, and e power minus of imaginary part of alpha I alpha j. And minus will come out of the imaginary inner product. Okay. Imaginary part. Okay. So this is okay. Yeah. I mean, if you want to put alpha j, alpha I, then it can be minus. Okay. Minus will come out. So this is okay. So minus will cancel and it's plus. So this is positive definite. Okay. So hence this function is positive definite. Whatever the function we have stated, that is positive definite. So we have proved the properties of the characteristic function. Now we have to prove the other way. Okay. Some allergy. Okay. AC is okay for you.
Today is just bad. I think.
No problem. These days we are not we are paranoid or something. Someone sneezes someone sneezed in the lift and we took it normally. So earlier it was not like that. Even I have some infection, so antibiotic. So okay, so we want to prove the other way. So suppose f is a function. Okay, now suppose f is a function from Cn to C. Okay, f of 0 continuous. Okay, f of 0 equal to 1. And this is positive definite. So this function, e power I, imaginary part of alpha beta, f of beta minus alpha. Okay, this function, k alpha beta, is positive definite. Okay. Then we want to produce something. So any idea how to proceed? I have given a positive definite function. You want to get a state on that. Okay. So, I mean, this positive definite is just defined on Cn. So you have to get a state on gamma of Cn. First, let us get it on some arbitrary Hilbert space. The idea is get it on an arbitrary Hilbert space, some state, something. Okay. And then use Stone-Von theorem to get it to gamma of Cn. Okay. Get some arbitrary Hilbert space. There you define the Weyl, some unitaries which satisfies the Weyl relation. then come back to, then use Stone-Von theorem to come down to Fock space. Okay. So how will you get the how will you get a Hilbert space if you have a positive definite? Yes, exactly. That's what we did in the last course. There is something called Gelfand pair. If you have a positive, I will recall that. So, do you know this theorem? There is if you have any positive definite function on some set, any set, then you can construct a Hilbert space. Standard way of constructing a Hilbert space. Yeah, this is a well-known thing. That is how one defines Hilbert. That is how one defines tensor product for infinite. Tensor product for finite dimension is easy to define. But if you want to define for a general Hilbert space, use this construction. Okay, you have to use. So if you look at my video where tensor product is discussed, this is discussed there. Okay, so this is the Gelfand pair. So or GNS construction. Okay, this is also called GNS construction or Gelfand pair, or it's also Kolmogorov construction also, because Kolmogorov also has done. Gelfand-Neymark theorem is a theorem in operator algebra which says any abelian algebra will look like, any abelian C-star algebra will look like continuous functions on some compact Hilbert space. That construction is more or less the same. The same idea is there. That is Gelfand-Neymark theorem. Gelfand-Neymark Siegel construction is there for any C-star algebra. That is, every C-star algebra, you can act it on some Hilbert space as operators. It's the same idea. The idea is you have a positive definite function, or if you have a state or something. If you have, there you have a state on a C-star algebra or something. Yeah. So then you define an inner product. You take that, whatever the set you have, take that, convert that into a Hilbert space, take some total span or functions on that. Then you define an inner product on that. If it is a semi-inner product, take the modulo. You just modulo out the zeros, where the inner product is vanishes. Then you get a Hilbert space. Then you get an inner product space completely to get that. Okay. So the same thing, GNS construction or Gelfand pair or whatever, Gelfand pair or Kolmogorov construction. It's also called Kolmogorov construction.
Because with Gelfand pair, you took the complex valued functions on the set. Right?
Correct.
But in GNS, you quotient the algebra itself. You make a.
No, the idea is same. Yeah, but there you don't need to take function because already you have a C-star algebra. No, the construction are different. The theorem is different. The construction is different, of course. GNS construction for C-star algebra this is for positive definite function are two different things. There is a connection between them. The theorem is statement is for this is for a statement for something else. This is a statement for some other object. So there will be difference in the construction. Basic idea is same. Okay. Or you can get a C-star algebra out of it here somewhere. Okay, it's possible. Anyway, functions. Yeah, using that function, do something and get a C-star algebra. All you have to do is define a norm and star somewhere. Okay. So GNS, by GNS construction, there exists a Hilbert space K, and a map alpha going to lambda alpha. Okay. Alpha is in Cn, lambda alpha is in K. Okay. So all these things are up to unitary. Lambda alpha, such that this lambda alpha in K, alpha in Cn, okay, this is contained in K, is total. Span closure is everything. Okay, that means the span, you take the span and take the closure, that is K. It's a total set. And such that, and lambda alpha, lambda beta, this inner product equal to K alpha beta, where K and other things are defined. Okay. So if we have a positive definite function K on two variable, K alpha beta, then you have a Hilbert space K where this alpha can be embedded, and the set, whatever the set where the function is defined, that set can be embedded as a total set of vectors. Okay. And the inner product between any two vectors is precisely this positive definite function, K alpha beta. That's all. So this is what is called a Gelfand pair. Okay, I'll finish it shortly. Become tired. because of antibiotic. Okay. So this is true. Okay. Okay, so now we got a Hilbert space K, and we got we got a Hilbert space K. Now define U alpha, okay, on this lambda beta by e power. So there it's plus, so I need minus imaginary part of. I'm feeling uncomfortable somehow. Shall we stop?
Yeah.
I'm sweating and feeling uncomfortable suddenly. I don't know why. I took some antibiotic, slightly strong antibiotic. So, yeah, sorry. Yeah, we'll meet tomorrow. Tomorrow also, I will have antibiotic, but let's see. We will be able to do it. Same time we'll meet tomorrow. Yeah, in the afternoon. After, yeah, so only started now.